So thanks a lot for the opportunity to come along and talk to you about the CERN experience with Openstack. If you're driving across the border between France and Switzerland, you might see this round wooden object to one side. That's the CERN Exhibition Center, and if you want to go and see the world's first World Wide Web server, it's inside. It still works. So a few words about me. I look after the team that does compute monitoring and configuration management at CERN. This is actually the view from my office. It's not everyone that has an antimatter factory just down the road from where they work. I've also been elected by the community to represent the community on the Openstack Foundation board. And for 3 years during an early start, as we gradually built up the feedback loop between the user community and the development community, I was also on the Openstack user committee. So what's CERN? CERN is a worldwide collaboration. The member states, 22 countries across Europe, and Hungary has actually been a member since 1992. But it's more than just the member states that are contributing. All across the world, over 100 different countries send physicists to come and work using the CERN facilities to understand fundamental questions. What's the universe made of? How does it work? Part of the way that we solve that problem is with the largest piece of scientific equipment on the planet. This is the Large Hadron Collider. It's just between the border between France and Switzerland, and you might be able to see the lake and Mont Blanc in the background to give you a feeling of the scale. What are we looking to find out? This is basically the history of the universe in a single slide. 13.7 billion years, the Big Bang, the subsequent expansion of the universe, and now we're able to start looking out through telescopes such as the Square Kilometre Array into how the universe is expanding. So what we're really looking to do is to create the conditions just after the Big Bang to understand the fundamental nature of what is matter made out of. As you go down from atoms, down to protons and electrons, down to quarks, what are the laws that control those and the interactions between them? Why is it that we're not half matter and half antimatter? Since the Big Bang was a huge puff of energy, those ought to be equal. And equally, why is gravity so weak? We don't really understand how gravity fits in with the rest of the model that was invented in the 1960s, the standard model. So the experiment itself, it's a 27-kilometer ring. And it consists of around 1,300 magnets, and these were lowered down 100-meter shafts and then constructed and put together in order to be able to create the magnetic fields that can steer the beams of protons as they go around in those two small tubes inside. It's actually one of the coldest places on the planet. It's about minus 271 degrees centigrade inside those tubes, so 2 degrees above absolute zero. We use around a quarter of the world's helium production when we're cooling this down, which occurs around once every year in order to be able to then get the magnets so they're superconducting. At the same time, we have tubes. These vacuums are evacuated to a level which is roughly equivalent to the moon. The aim behind that is there should be nothing inside the pipes that can interfere the protons from going around and colliding. And then in 4 places around the ring, there are these massive digital cameras. It's about 100 megapixel cameras. They weigh the same weight as the Eiffel Tower. So it's around 7,000 tons. And these are built by collaborations of thousands of physicists and engineers designing how the accelerator and the detectors are going to work. Unlike your standard Instamatic, these 100 megapixel cameras take 40 million pictures a second. This means that when you get the collisions, they're able to take rapid snapshots and follow the movement of the particles. This is about 1 petabyte a second in total that gets produced and has to be processed. Clearly, we can't handle that much data, so what we do is we filter the data down, removing the physics we've already discovered, and then with that we get down to data rates of around 20, 25 gigabytes a second coming into the computer center over high-speed networks. The data is then recorded. We put it onto tape. It's the cheapest medium in terms of bytes storage. And so we have around 200 petabytes currently stored on tape at the CERN Computer Center. It's about 90,000 disks, about 15,000 servers spread across the hall. But that alone isn't enough. We have to collaborate with 170 universities and labs around the world, and they provide us with computing capacity, with storage capacity, to be able to process the data. So CERN's main job is to record it and then distribute it to these other centers for them to be working on. So it's around 10,000 physicists that then use this facility to try and discover fundamental physics and hopefully arrive at Nobel Prizes such as the Higgs boson discovery in 2012. So last year we recorded about 55 petabytes of data, and this means that we're facing a continuous increase in the total volume of data. The aim is that no data is ever removed, but we continue to ride the wave and improvement in technologies so that we have data going right back to 1960. And the goal there is that if we discover something new, we want to go back and see if we could have found it in the previous experiment by looking over all of this data store. So how do we do that processing? 90% of the compute capacity at CERN is run on top of Openstack. The slide I made about 2 weeks ago had 312,000 cores. It's now up to about 320,000. The team like installing machines while I'm away just so that the slides are out of date and they can complain about it afterwards. It's about 38,000 virtual machines in total, and this covers the whole range of activities of the lab. It's not just the compute infrastructure, it's also things like the pension fund, the salary systems. And when you're running things like a salary system and your pension fund on top of the software, you want to be really sure it's solid. And it's been very, very pleased to see how things have been going. So looking back, in 2011, we were facing a major rethink of the way we delivered infrastructure. We were fortunate to have some funding from the European Union from 2001 to 2011 to build up a set of tools that would allow us to manage infrastructure at scale. This was a very useful learning exercise and fed into many of the open source projects that followed. However, the actual tools themselves did not achieve widespread community adoption. So we were faced with a scenario where the tool set was starting to get brittle. It was in Perl. 100,000 plus lines of Perl is tough to keep going. It's also tough to encourage people to apply for jobs with that as their main activity. At the same time, we were facing limits in terms of the computer center. It was built in the 1970s for a mainframe and a cray, and it just wasn't able to handle the density of power and cooling that was required for industry standard servers such as today. So what we did is we asked the member states of CERN to make us a proposal for a place where we could install additional computing capacity. We could not put any more on the CERN site because of electricity constraints. The data center itself is only 3.5 megawatts in Geneva, but the accelerator needs about 200 megawatts to keep it going. So at that point, we weren't in a position where we could be asking the accelerator to reduce the power consumption in order to increase it for the data center. So after asking the member states of CERN for proposals, the winning proposal was actually the Wigner data center in Budapest. So it's just up the hill from here. And I had the great pleasure of going to see it yesterday and meeting the team that's been running the infrastructure for us there. We have 300 gigabit links to make sure the two centers can be run in a transparent fashion, so the physicists do not know where their work ends up. And with that, we then have the OpenStack cloud spread across those two locations. However, getting the facilities was one thing. What we needed to do was also compete with the public cloud providers that the physicists were starting to have experience with. And there we were dealing with public procurement cycles. And this meant that we needed to be finding ways under which we could be delivering resources to users in the time of a cup of coffee, rather than waiting up to 280 days between asking for something and before it got delivered. It's a very formal process that makes sure that the purchases made by CERN are spread across all of the CERN member states in proportion to their contribution. But part of that process is also that it is quite formal, and therefore it means that there are steps to be followed. In addition to that, we're often dealing with scales. That means we find disk firmware problems, BMC issues, memory quality deliveries. And these are difficult to be tracking down. So sometimes we've had even a year between an initial idea before the deliveries are handed over to our users in production. And this was clearly something we needed to hide from the users. So around the same time, we were looking at various solutions. And we went along to an event in London because there'd been some talk about this new project started by NASA and Rackspace. And already it was clear that there was a vibrant community forming, and it was a good opportunity also to meet Jonathan for the first time. So I was sitting at the back, next door to some of the various distribution manufacturers and supporters, and it was very clear from there that the industry backing behind the project was coming along, as well as the interest from the research community. And that was a key part of us looking at the OpenStack adoption. It's finding that mixture of a strong community and also a viable business case that means that open source software can continue to develop. So I actually went back and did my first OpenStack Summit talk, which was in Boston in 2011. And it has some very aspirational statements in it. You're welcome to read it through and find out just how true we've actually achieved our goals. But it was a very good opportunity to reach out and evangelize with the community in terms of the use case that CERN has and how that could also contribute back. So we started off a formal project at CERN in 2012, and the primary goal behind that was to focus the effort in terms of getting the old infrastructure systems changed out and replaced by upstream open source communities where CERN would only have to contribute to the small improvements it wanted rather than have to write and maintain all of it ourselves. In particular, the staff numbers were fixed, so we could not hire any more people, but we knew how much the infrastructure was going to have to grow, so we had to find ways to automate and become more efficient. With the accelerator schedule, there are periods during which we do upgrades, and the long shutdown 1 was coming along in 2013, where we would have a 2-year window where we could make disruptive change to the IT environment. So we needed to get on quickly. We couldn't just wait. So we followed the classic open infrastructure approach. Now, at the time, these were very, very independent sets of tools, and over time, they've gradually coalesced, and more of the open infrastructure initiatives are getting these, so constructing tool chains such as this is a relatively simple activity. We selected OpenStack with the Red Hat Community Distribution, RDO. For monitoring, we chose Kibana, Elasticsearch, and Grafana. Puppet for configuration management, Ceph for storage, and then going to a full CI/CD DevOps mode of working with Git and Jenkins to do that deployment for us. And this is a crucial part of the delivery, which is you need to look at the whole chain to make sure that the entire transformation took place, rather than that only one area improved and not others. So we named our first OpenStack clouds after small animals that had short lifetimes, because the first part of setting up clouds involves doing test installations, trying out various techniques of deployment. I think the first cloud was called Guppy, which was a very small goldfish that tends to float to the surface. And this was around Diablo Essex time, and it was floating to the surface quite a lot during that period. But as we got to the end, we started to get a lot more mature. The final one that we deployed was the Ibex, which is a rather large goat that lives in the Jura Mountains. And that's been the model from which we've then been heading on into production. So from then on, and this was 2013, then we haven't had any virtual machines that we haven't been able to continue to maintain through multiple upgrade releases every 6 months. We added block storage. As a result of one of the summit discussions in 2011, I sat down at a table with Dan Bode, who happened to be from Puppet Labs, and he explained how Puppet could help out. We then sat down with Sage Weil, who was explaining how Ceph could help out. And with all these discussions that can go on there, it can really help to not only work on the core OpenStack part, but then add all these surrounding components that you need in order to deliver a genuine end-user service. And I had the chance to come along to Budapest in 2013 and talk at one of the Openstack Days here. And with a situation where we've got 1/3 of the cloud running just up the hill, certainly Budapest has a certain place in terms of the CERN infrastructure delivery. Production was 20,000 cores in 2013. So this was a start where we were allowing our end users to come in. We promised we'd be maintaining the environment for them in the future. We had support lines in place. We had monitoring. We had out-of-hours calls in the event of things going wrong. So this was then a robust service that the users could rely on. Since then, we've grown from 20,000 to about 300,000 cores. The size of the team looking after the cloud is the same as it was back then. This is what you need to do when you invest in the automation side. It's that you get to an order one scaling so that you can just carry on adding systems without needing to add staff afterwards. It required a lot of upfront investment, but much of that upfront investment is something that's completely reusable by other organizations. So people that are looking to build things now can be building on the work that's been done over the past 5 years by organizations like CERN. Ceph itself has grown now to 15 petabytes. It's more than just the block storage now. We've deployed the CephFS file system under Manila to deliver file shares. We've got the S3 and Swift interfaces to deliver object store. So that means the CERN user, when they come along to the CERN cloud, sees something which is a fully compatible infrastructure as a service solution for all of their needs. At the same time, one of the ways we can give back to the community is that we get deliveries every year. Normally it's of the order of 60 to 100 petabytes of storage, depending on what we need going forward. And we tell the physicists that the capacity will be a few weeks later on than planned, and then we phone up the Ceph development team and say, okay, time for a scale test. And we've done 3 of these so far. The last one was a 60 petabyte storage test. And clearly for an open source development team to get 60 petabytes of storage is not something easy for them to justify. But we can be providing short windows for people to come in and try things out. And then after that, they have a year to improve the software and come back. And then we can be using those improvements in the next step of the delivery. At the same time, our users have been very interested in containers. And as part of some discussions that we had initially with Rackspace and the CERN teams and the Kubernetes upstream organizations, then we put together an Openstack containers as a service functionality. And the aim behind this is that containers ought to be something that the end user can get as easily as a virtual machine, but should be within the same framework. So whether they're using compute resources with containers or whether they're using them with virtual machines, we should still be able to track exactly what they're doing. So the basic command, it's a single command, and you get Kubernetes sitting at the end of an endpoint. This is very much along the lines of the sort of Google GKE environment. You shouldn't have to go through and construct lots of things in order to get a Kubernetes environment. And as Jonathan mentioned, we've got 200 of these now running at CERN. So our users are definitely enthusiastically getting involved in this, and it's allowed them to have a very rapid onboarding in terms of a new technology. But it's not just containers. We're also then looking at how do we go about managing all of the compute resources in the computer center. So I mentioned that 90% of the compute is virtualized. There is, however, the storage side and the database side, which is not under the same umbrella. And what we wanted to be able to do was to keep track of every single resource that was used. We have this scenario at CERN where, for example, a student will start on a 1-year contract, get some hardware, work on it for a bit, and then leave. But unless we're very careful with the procedures to make sure that hardware is recuperated and reused, it can get lost. So we have what we call dark hardware scenarios, where we'll come along when we're doing retirements and realize that a machine hasn't been used for a year. And this allows us to keep track of that resource and set things like expiry dates, as we do on virtual machines, so that people get notified if they haven't given that hardware back in the time window they've been planning. At the same time, it allows us to be offering some reduced overhead. The compute itself is not too significant, but the storage I/O overhead that you can get sometimes with KVM can slow things down. And so this then allows us to be able to offer people who need bare metal performance, the high performance computing people with InfiniBand, low latency, they can be using that resource. So one thing we found as we were studying the virtual machines is that for a very large virtual machine, when you get to 32 cores sort of size, you actually get significant loss using the very default configurations. We needed particularly large virtual machines due to some combinations of scaling problems with the system that we were using to schedule compute work, which we've now retired, but these were the problems at the time. So when we benchmarked using some sample applications, we were seeing up to 20% loss for the worst cases. We then used a set of tuning combinations. What was interesting here is the tuning recommendations actually came from the telecom industry. The functionality for doing CPU pinning, NUMA, huge pages was something that the NFV community needed in order to get the maximum performance in a telecom environment. But the same set of code improvements could then be applied into an academic and research environment like CERN's. And so with this, we got it down to around 3% in terms of the total overhead. So the logical thing then is if we have containers with one click, we have a bare metal service, well, let's do containers on bare metal. So this is now part of the Magnum project. It has been implemented, a set of templates, so you can create containers right on top of the bare metal for those applications that wish to take advantage of it. And it's a good example of why having a number of projects around in the same software framework allows you to then combine them to produce a high-value solution for the end user. So we're currently looking to do this for the compute farms, gradually moving from a pure VM-based environment to a partial VM and partial container environment. And one of the tests that we've been doing has been to actually have a look at federating Kubernetes across the different parts of the CERN cloud, along with federating out into public clouds. So the demonstration that Ricardo Rocha gave at the OpenStack Summit involved setting up multiple Kubernetes environments and then linking them together so to the end user they look like a single framework. And this gives you a very powerful hybrid multi-cloud software environment to work in. One of the things that takes a lot of time for us is actually when the hardware arrives. So if you can imagine 6, 7 large lorries arriving, all unloading, it fills up the warehouse in no time. We start using the corridors in the data center. And the main aim is then to get that hardware as soon as possible into the racks and into production. So one of the things that we do as part of that is go through a thorough hardware burn-in. The aim is that if you look at the curves, then you'll tend to see a situation where hardware, when it first arrives, has a higher failure rate, gets more reliable as it goes through its lifetime, and then as it gets old and starts to get out of the warranty periods, then the failures start to arrive again, the bathtub curves. So therefore, in order to get the service as reliable as possible, it's vital to put a large stress on the machines as they arrive. And this allows us to find problems both with the hardware itself, but also systematic problems across the whole release. So what we do is we run intensive CPU tests. These cause the machines to heat up a lot. We then find problems with fans or cooling structures. So it allows us to be really sure everything's okay. The sort of tests we run are combinations of CPU burn, memory testing, scanning the memory, looking to see if we get any memory counts, and then we do benchmarking. And the reason for benchmarking is firstly so we know how fast the machines are and whether they comply with the promises that were made as part of the tender. But we recently found something where the top left core on the second processor in Intel dual motherboard system is actually very slightly slower than the other 31. And this is the kind of thing that with a set of data scientists who are used to processing and handling data can be identified and then reported back to the manufacturer. So there's firmware changes that are coming along as part of that operation too. We also find situations where, for example, sometimes the binning processors are slightly different speeds. Although they're all compliant with the specification, the hardware is very, very slightly different according to the manufacturing yields. So how are we going to be automating this further? We use the Mistral workflow as a service component of OpenStack as part of many of our standard operations, like creating new projects, setting quotas. We also use this for the personal VM expiry. So if you're just asking for a machine for test, you get set an expiry date of 90 days, and after that 90 days, you get a mail. The machine shuts down, stays shut down for a week, and then gets deleted. So we're already using this actively, but what we would like to be able to do is to then use the workflow as a service to actually do the complete process from machine arrival to machine retiring. And there are big chunks there, such as the burn-in test and the reallocation. The reallocation part is now done, and that's where someone asks for a machine from a pool. And what we now need to work on is the burn-in test and integrating all those other parts together. All of this is available on the CERN Ops GitHub repository. So anything that we are doing, we've written up as blogs, published or talked about in talks, and then you're welcome to come along and have a look at how we've done it in the CERN repositories. Pull requests welcome, but equally you might well find they're too CERN specific and you need to work on them a little bit for your environment. But it can help as an inspiration for you. Because we started early on, at the time, Nova Network was the only network component. This was before we had quantum and neutron coming along. And so we deployed a large amount of the CERN OpenStack cloud using Linux Bridge and Nova Network. Neutrons then come along. We've been using it. It's now running across the vast majority of the cloud. The difficulty for us is we wanted to maintain our promise that we would keep the VMs running. And to move from Nova Network to Neutron wasn't one of those operations where there was a formal description of how to do it. So we worked with a number of other companies who'd gone through the same operation. I think it was PayPal that had done a similar migration. And with that, we were basically having a VM running on top of Linux Bridge managed by Nova Network, and then a bit like changing the engine on an aeroplane mid-flight, we would then pull out the network and plug in Neutron underneath. So this operations, we're doing it gradually. It should be completed within the next 2 or 3 months. And then with that, the developers will finally be able to deprecate the Nova Network functionality with everyone on Neutron. At the same time, our users are asking for more flexibility. They want load balancing as a service. They want floating IPs. So we're starting to have a look at how we can be doing full software-defined network. CERN has a network with millions of devices. If you can imagine Internet of Things, and then imagine the accelerator trying to work out where the beam is, and then steer the beam and focus the magnets, it's a pretty complicated Internet of Things application, especially that we're steering something that is going just below the speed of light. So it's actually going around faster than electricity can send a signal. So with this, we want to be sure we have a stable network. So we're doing an overlay network based on tungsten fabric at the moment is the current solution. And then hopefully with that, we'll be able to give our end users the final piece of missing functionality compared to what they expect to have in infrastructure as a service cloud. We have busy days. If you can imagine quietly coming out of New Year's Day, relaxing after various festivities, and then reading the IT press and seeing, oops, there's a potential hypervisor breakout scenario coming along. So when we returned from our Christmas holidays, we sat down and basically went through the operations that says, okay, 38,000 VMs, 9,000 hypervisors, how are we going to do it? The firmware needed to be updated, the kernels need to be rebooted. This basically meant rebooting the entire cloud. The accelerator is shut down at that point because electricity is too expensive over the really cold bits of winter. So this gave us a great opportunity, but we had to move fast. So we set up waves where we did 1 day of reboot of 1/7 of the cloud, and then 1 day of resolving problems, 1 day of reboot, 1 day of resolving problems. And that meant we were able to get through it all by about 2 weeks. The automation for all this is now part of our standard tool set, so that means that when the next one comes along, then we'll be able to do it hopefully more smoothly. It was also a great opportunity to get some of the virtual machines up to date, because although it's bad to have the reboots, what's nice is you get the very latest QEMU and you get the very latest Ceph drivers. So for those virtual machines that have been running since 2013 without being rebooted, and there still were some, this was a great opportunity to have a reboot. At the same time as it's been a very interesting technical challenge, one of the things we've benefited from hugely has been the OpenStack community and interaction with them. Putting in place a cloud-based system isn't just a technical problem, it's also a cultural shift for people in the organization. The traditional approach of saying, I leave my software frozen until I'm then able to run a manual exhaustive test, and then I do an update, and then I leave my software frozen, has to change. The software is coming out too fast, too many different parts of the tool chain being updated at once. And the community has been very helpful in convincing members of the team that this is the way to go. They talk to other people, they see it works, they get that belief, and then with that they come back, and that helps to change the organization. The other good thing from the community side is many people at CERN are working on fixed-term contracts, so between 1 year and 5 years. And that means that people who come to CERN, arrive as a basic Linux admin, come away as OpenStack, Puppet, Grafana skilled peoples already with good contacts in the community. And that means these people are then going off to very, very highly paid and highly skilled jobs as part of the future. So it's very much part of CERN giving back to take advantage of that. Because we're an open organization, it's actually allowing us to be very public about what we do. And we really appreciate when people come back to us also and say, no, I don't think you're doing the right thing there. Because that then also allows us to work through, maybe we had a preconception about how we were doing things in the past that meant we weren't looking at doing things the right way. So looking forward, we're going to make the LHC more intense. The High Luminosity LHC will effectively increase the number of concurrent collisions going on in the accelerator at any time. So if you can imagine situation at the moment, we get about 70 collisions occurring simultaneously. That means that the software has to work out which one of those particles came from which collision. And this will then go up towards 200, 300 as we get to the High Luminosity LHC. This causes the computing to exponentially increase. And as a result of that, we're now doing the maths. We have to plan a fair amount further out, which says that for 2021, we'll be looking at around, 2024, we'll be looking around 1 exabyte of data. And then looking out further than that, we'll be looking to 5 to 6 exabytes of data a year. The computing scale is something like 60 times more than we have currently. Moore's law will get us maybe 1/4 of the way there. We need to find different ways of doing computing now. So we're looking at GPUs, we're looking at FPGAs, we're looking at ARM. All of these things can be incorporated into the OpenStack cloud and then allocated out for people to try things, along with the functionality that was mentioned as part of the Queen's delivery. Maybe we won't have enough resources on-premise between CERN and Budapest, so we're also starting to explore commercial clouds and have been doing a number of tests with organizations through a European Union project called Helix Nebula. One of the most recent ones has been with the T-Systems Open Telecom Cloud, which conveniently happens to be based on OpenStack. And that means that all of the tooling that we've got in-house could be immediately applied to the external cloud provider, a real benefit of API compatibility and consistency. But we also know there are other clouds out there too, and that's where federated Kubernetes is getting to look very interesting as a way of handling that multi-cloud world. Going forward, we're doing a number of pieces of work, both with CERN staff, but also we collaborate with industry, in particular with Rackspace and Huawei, through something called the CERN Open Lab. It's different from the Open Lab Jonathan mentioned previously. We just happen to use the same names. And with these, we take problems that the LHC is confronting us with now, work with industry such that when industry needs those solutions, they will be available for them, and therefore, at that we can know they've been tested on the CERN cloud, and chances are if they work on the CERN cloud, they will work in most environments. So we've been doing spot market. This allows you to opportunistically get virtual machines from spare capacity that's reserved to give elasticity, and this will allow preemptible VMs to be then terminated and committed work to be brought in of higher priority. Cells version 2 is the work that's been going on where this will allow us to build more scalable clouds, and those should be available for all users rather than only for a subset of those who can maintain a rather special branch of Nova. That's now available in production in Queens, and we started running that 2 weeks ago. Neutron, getting that to scale, switching over to software-defined networks. Getting Magnum so we can do interactive rolling upgrades where the user decides what level of Kubernetes they want to be running and when they want to upgrade it. Block storage performance with Ceph, trying to get that final extra set of IOPS out of the storage. Federated Kubernetes, I mentioned. And also we're now looking to work with the Square Kilometre Array. So as part of their work building these 2 large telescopes in South Africa and Australia, they're also needing to build large-scale HPC systems that they're currently looking to do based on OpenStack. And much of the work that we're doing with them is around areas of common interest. So this is big science working with each other. They have an even bigger data problem than we do, but they're a few years away from that yet. So, in summary, OpenStack's given us a very flexible infrastructure, which has grown from being a pure VM environment to providing a large number of functionalities around containers, bare metal. We're able to put together an open infrastructure toolchain, gluing these different communities together such that they can then interact and provide us with a final solution. The open source collaboration has been incredibly fruitful. The number of times we've come across things that we thought that we needed, and we've then found that other communities have already done and contributed upstream. It also allows us a very effective way of sharing and giving back, because every patch that we do is then available for you to be installing as part of your OpenStack cloud. However, looking out to 2023, there's still a huge amount of work that needs to be done, and that's why it's very great to come along to community events such as this and get people's feedback on how things are going, and thank you very much for your contributions.